Now we move towards quantum gravity. Now, quantum field theory can only be formulated perturbatively. Probably you will see it in other courses. We will have to give only a few details of it because it deserves a course in itself. But we will cover what's necessary to move on. But one basic thing is that we have no idea how to define quantum field theory non-perturbatively. What does it mean? Well, in classical physics, we have an action, and out of that action, or Lagrangian, we derive field equations. Then the solutions of the field equations might sometimes be difficult to work out, and often we use approximate methods. But at least we have the equations, and the equations are exact. Nothing like that exists in quantum field theory. And so you may ask yourselves, what are we approximating when we do perturbation theory? Normally you perturb around something, but you need to have a guiding principle, the equations at least. Well, we perturb nothing here, actually. We try to build the theory quantum after quantum, interaction after interaction, as it should be, because this is nature. And often this building without any light leads to problems. And you have to solve those problems as long as you find them. Those are then the problems that could be solved in the standard model and all interactions but gravity. And for gravity, we will see actually that we will move forward and we can also solve them for quantum gravity. But at the end, what we only have is a perturbative theory. Nobody knows how to solve those problems non-perturbatively, and despite many people use non-perturbative, this word, to describe what they do, they don't, because even numerical methods, being on the lattice, being numerical, are not non-perturbative. So everything we know about quantum field theory is an approximation in some way. And in the case of gravity, the perturbative expansion has to be defined around flat space. So we start with this, the perturbative expansion around flat space. First at the classical level, and then we will see the quantization. It should be remarked that perturbative quantum field theory is known very well, actually. And although probably we won't cover it here, many of the properties we know about in quantum field theory can be proved to all orders in the perturbative expansion. And it is also very successful because the standard model is very successful. One of the most successful theories ever, actually. In gravity, there are additional problems, not to say that the problems of the perturbative construction of quantum field theory were less difficult in QED or the standard model. But the difference is that in QED or the standard model, particularly in QED, you could do experiments. And that was helping a lot in order to discard all wrong paths and get a hint from nature about what to do. In gravity, we cannot make experiments. Quantum gravity, of course. So the perturbative expansion means that we consider the flat space metric, and every metric will be a fluctuation of the flat space metric. We will parameterize the fluctuation like this. So basically this phi mu will be what we will call the graviton, or the field that will propagate the graviton. The inverse metric, of course, will be eta mu nu minus 2k phi mu nu plus orders of phi squared, and for the moment we will not care about the higher orders. And now we understand that in the flat space expansion, indices are raised and lowered with the flat space metric and not with G mu nu. Let us work out the action to the quadratic order in phi, because the first contributions, the most important one, the free field limit, which will be the first thing to study, are given by the quadratic part of the action. And we wrote the action in many forms. We will use this one, the gamma-gamma form. Why? Because it's very easy here to go directly to the second order contribution, because gamma is first order in phi. So gamma-gamma will be second order. G will be replaced by flat space metric. Square root of G will be 1. It's rather easy. So let's first study the expansion of gamma mu nu rho. That is 1/2 G rho sigma partial mu G nu sigma plus partial nu G mu sigma minus partial sigma G mu nu. Now, since these matrices are under partial derivatives, eta doesn't matter, because eta is constant. So those derivatives become derivatives of phi, and that's already first order. So to the first order, we can replace this metric by 1, the identity. So we can write 1 divided by 2, factor 2k, which will simplify the 2. That's why I introduced the 2k, and for other reasons. And then we'll just have partial mu phi nu rho plus partial nu phi mu rho minus partial rho with the upper index, which means that it is raised by means of eta mu rho. Phi mu nu. Plus higher orders, and we do not need those higher orders for the gamma-gamma action, because this is the gamma-gamma action. So this goes into eta, this goes into 1, and these two will be replaced by that thing. There are other simplifications, actually, that we can make. Why? Because sometimes you have a relatively simple combination, which is a gamma with 2 contracted indices. Let's work that out separately. And this one is also simple, because this one has those 2 lower indices that will be contracted by eta. So both are rather peculiar. Let's write them down. Let's contract rho and mu there. let's say lambda lambda. If we contract rho with mu, so these two get contracted, these two get contracted, and these two get contracted. Well, observe that the first and the third will cancel, so you just remain with the middle one, and that gives partial. Oh, I was contracting nu with rho. Okay, so if I contract nu and rho, only the first one, where I write phi. Well, let me first add higher orders, where by phi I mean the trace. So when I contract nu with rho, this and this cancel out. So this thing is very simple. Then there is this other one, gamma mu nu alpha with the contraction of eta mu. So if we contract mu and nu here, you have mu and nu, twice the same contribution, and here you have a trace. We just have to, it's not a great simplification, but we have to write it down. So twice d mu phi mu rho minus d, so we have contracted mu and nu, d rho phi, partial rho phi. Or let's stick with k outside. K, it's better. What about the second terms here? Here there is not much we can do, because alpha, they are contracted in all awkward ways, so there is no self-contraction, and that is the most important thing we will see, because that is really what propagates the graviton and not the others. So we calculate what we get. S gamma gamma is equal to 1 over 2k squared, but the k squared we can simplify, that's why we put k's here and there. Here there is a k squared, here there will be 2k's from both gammas, and so they simplify, and in the quadratic part we will have no constant. Square root of g is 1, g mu nu is eta, and so in the first case we have to contract the two objects just computed. D mu phi partial mu phi times partial, we have to change names of the indices, partial nu phi mu nu minus partial mu phi. And that's the first. Minus 1/2, minus because there is a minus here, so minus 1/2 integral d for x of what? We have to just write the two gammas, these two gammas, mu alpha lambda partial mu phi alpha lambda. The arrangement of indices, the structure is the same as the one of the Christoffel symbol, so it is fairly easy to remember it. This is it. Oh, I forgot to say, phi mu nu, of course, is a symmetric matrix. We are working in the metric formalism. If we had to work with the Filbane formalism, we would have to expand the Filbane around flat space. That would take a little bit more effort, but with fermions it would be necessary. But for the gravitational part, since there is no Filbane that's necessary, you can do this, and then, if you want, you can relate the result directly to the one you would get by expanding the field by around flat space. So this is the first gamma, and the other one is nu lambda alpha. So nu lambda alpha plus lambda nu alpha minus alpha nu lambda. Okay, now it's just a matter of doing what we have to do, and several things will simplify. You could, for the moment, expand directly the field equations, the Einstein equations, which we will also do, but we don't, because in that the expansion would be enough for classical gravity. This, the action, will also be useful for quantum gravity, because for quantum field theory you need the action and not just the field equations. So you have 1/2 integral of d4x. The first two terms here can be maybe written in some better way. No, I don't think so. Let's just copy what we get. Yeah. We will use partial integrations to simplify some things up to boundary terms, but for the moment I don't see anything we gain by making partial integrations. We just copy the first term minus the second term, which is a sort of kinetic term for the trace, you see. It's a kinetic term for the trace with a wrong sign. That's a peculiarity of gravity. It has to have the wrong sign, but it does have the wrong sign. Other terms like this will come from the second part. So from the second part you have minus 1/2. Let's multiply this by that. We have partial mu phi alpha lambda, partial, oh yes, one thing I forgot was the eta mu. So nu is actually raised, and it is equal to mu. So all three indices are contracted, raised. Mu and mu. Okay, so the first term is partial mu phi lambda alpha, and that is the dynamical part. It's like the one that will, after the partial integration, that's a box. So that's the wave equation, the D'Alembertian. The others are just there for gauge invariance, basically. So all the others are there for gauge invariance. So probably there is another term that will be equal, because, well, let's do it mechanically first. So the second is partial mu phi alpha lambda, partial lambda phi alpha mu, minus partial mu phi alpha lambda, partial alpha phi mu lambda. And we have done this multiplication. As far as the multiplication of the second term by this, let's look at it. You will have, well, maybe we can just do it, because I think you don't see it automatically. When you have some experience, you know what you get, so you can use shortcuts, but if you don't, you just have to do everything. So the three terms are these, minus partial alpha phi mu lambda, partial alpha phi mu lambda. And that's another box, actually. And the third one, minus partial lambda phi mu alpha, partial mu phi lambda alpha, minus partial lambda phi mu alpha, partial lambda phi alpha mu, or mu alpha, minus plus partial lambda, the last one, mu alpha, partial alpha phi mu lambda. Now let's see what we can do. Let us isolate those that have a box. That means the two partials with the same indices. There is one because the others can be like this or like that. There is nothing else. So those are the two most important terms, actually. So let's isolate these types of terms. We have one here, we have one there, and we have one here. So I guess I forgot the minus sign everywhere, because otherwise you realize that this is 1 minus minus, so it would be minus 1. The wrong sign there cannot be. We will see what the right sign is. So I forgot that minus sign, which means that in all contributions there, I have to change the signs. So, well, it's very easy because instead of being plus plus minus, it is minus minus plus, and the last line is the contrary. So minus minus plus, minus minus plus, plus plus minus. Okay, so these three terms give the most important term. With a plus sign. Partial mu phi mu rho, partial mu phi mu rho. These three terms with a plus. Then there is this one which has a minus. Minus partial mu phi, partial mu phi. Then we will simplify the others by means of partial integrations. So let's check, for example, if there are other terms with a trace. Only this one, so that we can copy because the others will never give traces. Plus 2 partial mu phi, partial nu phi mu nu. And we have done that. Let's see if there are some simplifications. Well, I anticipate all the others are the same term. All the others are the same. So we are looking at this, and this. You can check that these have the following properties. The partial integrations are contracted with one index, and the other partial integration is contracted with another index, with an index of the other phi. So one partial integration is contracted with one index of phi, and the other partial integration is contracted with an index of the other phi. And it doesn't really matter. You can exchange those two partials by partial integrations. two partial integrations don't give any minus sign, so you could write lambda and mu there. Now you realize that all these terms are the same, because here you see mu, mu, lambda, lambda, and the remaining integers, sorry, mu, mu, alpha, 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 mu, mu, alpha, alpha, lambda, lambda, alpha, alpha, lambda, lambda, and so on and so forth. Lambda, lambda, no, this one was the other type, lambda, lambda, mu, mu. They are all the same. And so you have minus, plus, so you can drop those, minus, minus, plus, minus, which means minus 2. It doesn't go away, you have minus 2. Minus 2 of what? Partial phi, partial phi. You can write it like this. You have to contract the partial with one index. You can write it like that. And that is it, plus cubic orders. So that is the quadratic part, and that's the starting point. Let us work out the interaction to the lowest order. What do we mean? This, J mu A mu, which in our case will be the stress tensor of matter instead of J, and instead of A, phi mu nu. So that will be T mu nu phi mu nu. Well, we already know what it is, but let's derive it. And again, we focus on the bosonic case because it's simpler, but with what we have worked out so far, if you will need it, you will have all the information to do the same for the field bind case. It's just a little bit more work, but conceptually there is something, actually, because there are local Lorentz symmetry transformations. But anyway, this is the definition of the stress tensor that we have given for the matter part with so let us replace G mu nu by that. That means that we can write T mu nu as minus 2, let's say square root of G is 1 to this order, because we want because we will see that it is the lowest order here that matters is the 0th order, because T mu nu will also by itself be multiplied by phi, so it's enough to work out the 0th order. But we will see it from the result in a moment. Anyway, the differentiation with respect to this is equal to 2k differentiation with respect to phi. So you have a 2k in the denominator, and you can write this. Or you can turn it around, plus higher orders. You can turn it around and say that the derivative of Sm with respect to phi mu nu is equal to minus k T mu nu plus higher orders. And then we integrate this equation. This is a derivative, functional derivative. Derivative is basically the same, because we know how the action is built, and it has to be local. So basically, Sm, we can see Sm as a function of phi. It's a functional, but again, there are little details basically. And you can Taylor expand it around phi equals 0. Phi equals 0 is flat space. That's what we are doing. We are doing a Taylor expansion around phi equals 0. So Sm of phi will be Sm of 0, constant, I mean the kinetic part of the matter, which will not depend on phi by definition, plus phi mu. The first order of the Taylor expansion is this, plus the rest. But we know this derivative, and so we know how to write Sm0 minus k t mu phi mu. And that's it. That's how matter. So this could be the kinetic term of matter. So it could be everything that does not contain gravity. So the flat space matter action. We can write it down here. Flat space matter action. Which will not really be important for the moment. And so when you want to add to S gamma gamma this thing plus T phi, you can work out the field equations then by taking the variation to the lowest order of this action with respect to phi. This will be the expansion of the Einstein equations to the lowest order, which we will later work out as the expansion of the Einstein equations to the lowest order. We are not now doing this with the action because, again, at the quantum level, that's important. So let's say that we consider SH plus SM, and of course, if you want, not particularly difficult to do the same with the expansion if you add a cosmological term, but there is a subtlety with the cosmological term. That's why we didn't introduce it. That actually the flat space metric is not an extremum in the presence of a cosmological term. So it's not, I cannot say a minimum because there is no minimum in gravity of the action, and well, not even in a non-relativistic mechanics you can talk about a minimum because it's T minus V. The Lagrangian is the difference between the kinetic term and the potential term and are both positive in general. So cannot really talk about a minimum, but an extremum. And in the case of the flat space metric, that is a solution of the vacuum field equations only if lambda is 0. Because if G mu nu is flat space, that's 0, that's eta, lambda should be 0. So G mu nu is equals eta mu nu is a solution only, so remember this was very, very important, only if lambda is equal to 0. And you can say, but lambda is not 0 in the universe, probably. And actually there is no reason why it should be. So what we are doing is, well, it's one of the many things you have to deal with when you study gravity. So this is a digression, but we forgot to say it earlier. We work at lambda equal 0. For a reason, this reason. So if you want to collect the two contributions to the lowest order, one is this. And the other one is just that. So the other one is minus kt mu nu phi mu nu. Here it is minus 2k t mu nu phi mu nu. Plus, of course, higher orders in phi. Field equations. We take a variation with respect to phi, and by means of a partial integration, this thing goes to the other side, and there is a minus. The variations with respect to both give the same, and that drops the factor 2. So the first contribution just gives box phi nu rho. And the second contribution, how to do the variation there. Remember that phi is eta mu nu phi mu nu. And so when you vary with respect to phi, you remain within eta. So the second term here gives the 2 drops again, plus, sorry. In the first one we have a partial integration, so we have a minus, and in the second one we have a plus after the partial integration. Now these 2 terms are not symmetric, so here we cannot just drop the factor 2, but there is a 2 in front that drops the factor 2 by itself, but we have 2 contributions. And so the first one will be a minus eta, okay, this is nu rho, first is minus eta nu rho, and then this object, which is partial mu, partial nu, phi mu nu. We have varied here. Now we vary there. And that will give, again, a minus. But now the 2 indices are on the partials, because phi cannot have indices. Then there is this thing. These 2 factors are symmetric, so that cancels the factor 2, but we have another factor 2. So here the factor 2 will remain. The sign will change because of the partial integration. And when we go there, let's see, we have partial phi. One index is contracted like that, and the other ones instead are like this. And now you understand why that factor 2 remains. We cannot leave it like that, because we are taking the variation with respect to a symmetric matrix, so the result should be symmetric, which means that we have to write 2 terms and no factor 2. Partial mu phi nu mu. Finally, we have, oh yes, this, and that is kt mu nu. Kt mu nu with minus, so that is, you can write it like that, equals k t mu nu. T rho nu rho. Variation with respect to phi nu rho, so this is the equation. Let me check it, because it will be every sign here is important. By the way, if you want, you can check that this is gauge invariant to the lowest order. We'll have plenty of time to do that, so it's not need to rush, because this will be part of the discussion now to study the gauge fixing and get to the physical degrees of freedom propagated by gravity, which are the two helicities of the graviton. So let me check the signs. Plus, minus, plus, minus, minus, plus, and plus. Yes. But if you want, you can also do the same by expanding around flat space by expanding the field equations. So maybe we can move to another page. At the classical level, we could have just worked with the field equations, and it would have been simpler actually, because we have the expression of the Ricci tensor in terms of gamma. Here it is. And you see, if we expand Ricci, these two terms go away because they are quadratic. In phi, these are linear. They are the only ones that are interesting for us. And we have the expansion of gamma, so that is also straightforward. Let's do it. So in the expansion of gamma, you have k times this sum of derivatives. And the arrangement of indices is the same as in the Christoffel symbols, relativity connection. So apart from a factor k that stays out, you have partial mu. Then this is partial nu phi rho mu plus partial sigma. This is sigma phi nu mu minus partial mu phi nu sigma. Second one, partial sigma, partial, well, that thing is simpler. That thing we know already, because it's contracted. So it is just k d mu phi, k partial mu phi. So this thing we already know, k is there, and we remain with partial nu phi plus phi squared. So, okay, let me collect a little bit some things. Let me first write that term because it's a box, the Lambertian. It's more important than the others. Then I write the last term. And the other two, there is nothing to simplify there. And so we have to leave it there. Again, to write the equations, here we just put the flat space metric because it multiplies R, which is already linear, and R is easy to find because R is G mu nu r mu nu, but that means that we contract mu and nu, or nu and sigma there with the flat space metric, because g mu nu here can also be replaced by the flat space metric to the lowest order. So you get k minus box phi, you trace, minus box phi twice, plus d partial nu phi mu nu. That is R. And now we get back to the field equations that we wrote previously. So R mu nu is that. Factor K gets collected. Partial sigma, partial mu, phi mu nu, minus 2, so there is a minus 1/2 in eta and a 2, that is minus eta, minus minus is plus, plus eta nu sigma box phi, minus eta nu sigma, let's say partial alpha, partial beta, phi alpha beta, and that is equal to k squared t mu nu sigma, which means that 1k goes away as it should be. So just to check that the two boxes, one has minus, the trace one has plus. Where was it? One has minus, the trace one has plus. The other trace part is minus. Here it is. Then there is the other eta part. The other trace part is again minus, partial, partial here. And the other two terms are plus. So we are happy because the two things give the same. What about the gauge transformations? How do we expand it? How do we perform the gauge fixing? Let us recall what the gauge transformations are. The Lie derivative of the metric, which you can write, we will redefine this psi rho. So I don't remember if I use plus everywhere or minus everywhere. Probably I use plus. And so we continue to use plus. Plus and then when we expand, what do we get? The variation, so let's say that this is the variation of eta mu nu plus 2k, the variation of phi mu nu, 2k phi mu nu. So the variation of eta is 0 because that's a constant. You have 2k, the variation of phi mu nu. On the left-hand side. And on the right-hand side, you just expand that. Here you have the derivative of eta plus 2k. The derivative of eta is 0. So you have 2k, the derivative of phi. And that's already 1 to the first order, which we will actually drop, because here there is a more important contribution which will contribute which is the relevant one for the gauge invariance of the first order field equations, and that is the zeroth order of the transformation, which amounts to replace here eta, the flat space metric. And when you replace eta, those terms are just so that is what you get. So to the lowest order, delta phi mu nu is equal to, apart from a 2k, constant 2k that we can incorporate into psi, if we redefine psi, and we will redefine it, yes. This is the lowest order transformation, and if you want to check that the field equations are invariant, please do it. The right-hand side, the left-hand side is invariant, and the quadratic part of the action is also invariant under those transformations which are analogous to the transformations of QED, the gauge invariance of QED, which is just a derivative of something. That is a symmetric derivative. And actually, you can build this action, which we derived, as the unique action that is quadratic, two derivatives, and invariant under those transformations. The same way as you can build the QED action as the only quadratic action in derivatives, quadratic in derivatives and quadratic in the gauge potential, that is invariant under the gauge transformations of QED. So this is the very important lowest order transformation, gauge transformation of gravity. Let's stop 10 minutes.